Our last section on probability is about expected value. So here's how we find expected value, which I'm going to abbreviate EV. You take the value of the amount, of a particular amount, and multiply by that value's probability. Add the value of the next amount and multiply by its probability. And keep doing that until you multiply all the possible values and probabilities. Now that might not make a lot of sense how I've written it there, but let's look at some examples and it should. Suppose a coin is being flipped 4 times. And X is the number of times that the coin is heads. It says determine the outcomes or the sample space. So we've got to list out all the possibilities of 4 coins first here. So we could have heads, 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 heads. We could have heads, 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 tails. Then heads, heads, tails, heads. Heads, heads, tails, tails. We could have heads, tails, heads, heads. This is going to get old very quickly. Heads, tails, heads, tails. Heads, tails, tails, heads, and heads, tails, tails, tails. Okay, I think that's all the ones that start with heads. Now we'll just repeat the same with tails up front. So tails, heads, heads, heads. Tails, heads, heads, tails. Tails, heads, tails, heads. Tails, heads, tails, tails. Tails, tails, heads, heads. Tails, tails. I don't know what I sound like here, but it's silly. Heads, tails. Tails, 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 and heads. And last, finally, tails, 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 tails. Okay. So the sample space is not this because it says X is the number of times that the coin is heads. So what's the number of times that each coin is heads? Well, here there's 4, 3, 3, 2, 3, 2, 2, 1, and then 3, 2, 2, 3, 2. Oh, I think I'm kind of the wrong thing. Yep. Okay, heads. 1, 2, 1, 1, and no heads. So the sample space would be all those numbers, actually. 4, 3, 3, 2, 3, 2, 2, 1. 3, 2, 2, 1, 2, 1, 1, and 0. There we go. I'm going to take this to the next page with me because I'm going to need it. So next it says, complete the table with the probabilities for landing on heads using the sample space that we just found. So I'm going to paste my sample space here. And to find the probability, we need to know how many total numbers there are here. There's 16. So what's the probability of getting no heads? Well, there was only one situation with no heads. So that's 1 in 16. The probability of getting 1 head. So there were 1, 2, 3, 4 instances where we had 1 head. So that's 4 in 16, or 1/4. the probability of getting 2 heads. So there's 1, 2, 3, 4, 5, 6. 6 out of 16, or 3/8. Then there's 3. So 1, 2, 3, 4. 4 out of 16, or 1/4. And how many times did we get 4? I'm running out of colors. Once. So 1 in 16. So here's how we would find the expected value. We take each of these and multiply. Multiply, add it to these multiplied, add it to these multiplied, and so forth. So we've got 0 times 1/16. So there was, so getting 1 head had a probability of 1/4, which I'm going to leave it as 4/16, and you'll see why, because when we have to add all these, we wouldn't have to find a common denominator. We'd already have it. So we'd have then 2, and the probability of getting a 2 is 3/8. 3 times the probability of getting a 3 is 4/16, plus 4 times, and the probability of getting a 4 was 1/16. So then we just simplify. 0 times 1/16 is 0. 1 times 4/16 is 4/16. 2 times, I meant to leave that as in 16s. So 6/16. There we go. So we just multiply the times the top. 2 times 6 is 12. So 12/16. And then the next one, 3 times 4/16. 3 times 4 is 12/16. And the last, 4 times 1 is 4/16. And so we just need to add our tops. 4 plus 12 plus 12 plus 4 is 32/16, which is 2. So what's the expected value for the number of times you get a head? It's 2, which, so you should expect to get, if you flip 4 coins, you should expect to get 2 heads and 2 tails, right? That's what we would expect to have gotten for the expected value here, right? So again, that means that we expect to get 2 heads if we toss 4 coins. Let's try another one. A local club plans to invest $9,000 to host a baseball game. They expect to sell tickets worth $16,000. However, if it rains on the day of the game, they will not sell any tickets, and the club will lose all the money invested. If the weather forecast for the day of the game is a 30% possibility of rain, is it a good investment? So there's 2 possibilities here. Either it's going to rain or it's not. It wants to know what are the outcomes. Now the outcomes are how much money you're going to get or not get. So there's the possibility that it's going to rain and they're going to lose $9,000. Or there's the possibility that it's not going to rain and they're not going to gain $16,000. Okay? You see why I'm saying that? Because they've already invested $9,000. So we have to subtract off $9,000 to get 7. So our 2 outcomes is that they could lose $9,000 or they could gain $7,000. What's the probability for each event? Well, the probability that they would lose this money, there's a 30% chance, so we'll change that to a 0.3. And the probability that it won't rain would be 1 minus 0.3, or 0.7, 70% chance that it won't rain. So over on the next slide, we're going to put these outcomes in where we're losing $9,000 and its probability was 0.3, or where we're gaining $7,000 and its probability was 0.7. It says find the expected value. So we just multiply across and add like we did before. So we could lose $9,000 and that probability was 0.3. Or we could gain $7,000 and its probability was 0.7. Multiply. And the expected value is $2,200. So the question is this a good investment? Well, they didn't come up in the negative, so yes, it would be a good investment because they are projected to gain money. Now, this isn't saying that they are going to come out with $2,200 at the end. Understand that. It's not saying that they can expect to gain $2,200. It's just telling them an idea of whether or not this is a good idea. Whether or not it's a good idea to have the gain with a 30% chance of rain. Example 3 says you draw one card from a standard deck of playing cards. If you pick a heart, you will win $10. So there's one of your outcomes. Winning $10. If you pick a face card, which is not a heart, you win $8. So that's another outcome. And if you pick any other card, you would lose $6. So minus 6 would be another outcome. Determine the probability for each event. Well, we need to see what's the probability of drawing a heart. Well, a quarter of the hearts, there's 13 hearts in a pack of 52 cards. So 1/4 of them are hearts. And I'm going to go ahead and bring this down to my table. Then it says, what's the probability of picking a face card, but it's not a heart, okay? Face card that's not a heart. So let's see, how many face cards are there? There's jacks, queens, and kings, right? And there's 3 of those in each suit. So that would be a 12 total. But then 3 of those are hearts, so we'd be left with 9 face cards out of the 52. And then all the other ones, we could try to figure that out, but the easiest way would be to say, well, it'd be 1 minus the probability of the hearts minus the probability of the face cards that aren't hearts, right? We just subtract all those. And I'm going to leave that as 13 over 52, so we have a common denominator. And change the 1 to 52 over 52. So 52 minus 13 minus 9 is 30. does reduce to 15/26. And then part D is going to ask us to find the expected value. I'm going to stay here since everything's in front of me. So we'd have 10 times, and again, I'm going to keep the 52s to stay with a common denominator. So 10 times 13 over 52 plus 8 times 9 over 52 plus negative 6 times 30 over 52. 10 times 13 is 130 over 52. 8 times 9 is 72 over 52. And negative 6 times 30 is negative 180 over 52. 130 plus 72 minus 180 is 22. We don't want to leave that as a fraction because we're talking about money, so we want to put that in decimal form, and it ends up being 42 cents. So the expected value here by playing this game is 42 cents. Now again, that's not saying that if you play this game, you will gain 42 cents. By no means. Not if you just play it once. If you play it many times, then the average that you could expect may be 42 cents. What this again helps us see is that it is, slightly in our advantage to play the game. So since we come out with a positive number here, it means it doesn't hurt to play this game. So let's look at one more. It says Katie pays $10 to play the following game of chance. There's a bag containing 12 balls. 5 are red, 3 are green, and the rest are yellow. Katie is allowed to draw one ball from the bag. If Katie draws a red ball, she'll win $14. If she draws a yellow ball, she'll win $12. What is the expected value of one game? So to determine the outcomes, well, first off, she's going to pay $10 for this to play this game. Okay? So she's already losing $10. And then there's the possibility that, let's go ahead and say, and there's a 100, if she's playing this game, then she is definitely going to lose the $10. So the probability of her losing $10 is 1. Then the next outcome would be that she wins $14. And she would win $14 if she draws a red ball. So we need to know the probability of drawing a red ball. 5 or red out of the total of 12. So the next probability is 5/12. And then last, she could win $12 if she draws a yellow ball. It says the rest are yellow, so we're going to have to figure out how many yellows there are. There's 12 total, 5 of them are red, and 3 are green. So if we subtract there, then that means that there's 4 yellow balls. So the probability of a yellow is 4 in 12, or 1/3. Says create a table, so I'm going to have to draw my table this time. We'll have the outcomes, and the probability. And we've got to have 3 rows here. It's not too bad considering this app doesn't change my lines to be perfectly straight for me. Okay, so the outcomes was where we could lose $10 and that probability was 1. We could gain $14, that probability was 5/12. Or we could gain $12 and that probability was 4/12 or 1/3. And so to find our expected value, we'll multiply. So the outcome of losing $10, that probability is 1, plus the outcome of gaining $14 times the probability of 5/12, plus the outcome of gaining $12 times its probability of 4/12. So we'll have -10 plus 14 times 5 is 70/12. And 12 times 4 is 48/12. We need to change this -10 to over 12. So that would be -120 over 12. So -120 plus 70 plus 48 is -2 over 12, which as a decimal is -0.17. So what this says here is that your expected value is to not get -17 cents. That's not possible. But to lose 17 cents. So would this be a good game for you to play? No, it's not, it's not losing a huge amount. So you still got probably a good chance of winning something. But you definitely have a greater chance of losing than you do of winning. Then it says, what is the expected value of 100 games? And so this, we just multiply our expected value of -0.17 times 100. That's all we do. And we end up with -16.67. So if you played this game 100 times, you would expect to lose $16.67. So again, most likely, there is a greater chance of you losing here, but it's not huge. But obviously you're not going to, you can't expect that you will lose exactly 17 cents playing one time. In fact, that's not even possible. But this tells you an idea of whether or not it's a good game to play. Okay?